Thank you.
Uh, our next speaker is Nathan Giha. Nathan, I think I saw you log on.
So,
Go ahead and share your screen.
yeah. All
Great, we
right.
can see it. I can hear you. Yep. So Nathan is a student here at Michigan. He just finished his first year of his PhD, and he's going to talk to us about a palm-sized adaptive neutron scatter camera. Nathan, go ahead.
All right, let's dive right in. So, starting out, some introduction and motivation for why we'd want a palm-sized neutron scatter camera. Emergency responders and warfighters need an instrument for locating special nuclear material, and neutrons are an excellent indicator for the presence of such material, either spontaneously or when actively interrogated. SNM will emit neutrons. And in order for it to be useful to these people, we need it to be human portable, which means that it has to be compact, low power, lightweight, and rugged. There are some comparable imaging systems that attempt to complete these goals, such as the H2DPI you see on the right image here, that's composed of steel beam bars coupled on either side to silicon photomultiplier arrays. But what we're looking to do here is to miniaturize that even further. So we're looking at what you might see in the left image, which is a cube-based neutron imager. And in addition to performing its imaging capabilities, it's also a good opportunity to study lever arm distributions, which I'll talk about in later slides. So a quick review of neutron backprojection. We're looking for double scatter events that produce probability cones, which is where we think the source might be. And the way that it works is that we have a source, the blue circle here, it emits a neutron, scatters in one cube. We get the energy deposited, the location of the cube, and the time that it occurred. It scatters in another cube. This is our double scatter. We get, again, the position and the time of the interaction. And using basic neutron kinematics, since we know how much energy was deposited, and we know the time of flight energy, or the energy after its first scatter, we can reconstruct the scattering angle and therefore create a probability cone. And you can imagine if we overlay many of these cones, all coming from the sources in our field of view, then we could see something like an image like that, where the hotspot is our source location. So applying this to our palm-sized imager, here's a bird's eye view on the right here. We have 6 by 6 by 6 millimeter cubed organic glass cubes, all coupled to a Sensel SciPM array. And what you'll notice is that we get radiation coming in from a source up above. It scatters. We get our scattering angle, and we make a cone. But we have a very limited number of scattering angles in this case. For example, from pixel 4 to pixel 21, we have this very specific angle, and that's replicated all around the system. Another is 4 to 23, and we get a little bit of a harsher scattering angle. But basically the point is, we're only getting a few different kinds of cones. They all kind of overlap on each other, and so our images look something like this. Very heavily artifacted. We can see our hotspot, but the resolution in the altitude direction is really very bad. And so in order to make this an effective imaging system, we need to be able to increase the number of scattering angles, since we're very limited in our what I will call our lever arm distribution now, or these axes between in the flight path of our detector. So one way that we can do this with our totally planar cubic system is to vary the angle between our detector plane and the radiation flight path. In other words, entirely tilting the system relative to the source. So our total scattering angle given by alpha here is given by this relation. And so if we're able to continuously change phi, our altitude angle, then we'll be able to get a continuous distribution of lever arms and therefore get rid of those artifacts that we were seeing in the image in the previous slide. So modeling this detector in MCMPX Polimi, we have 8 organic glass scintillators arranged like so, and we tilt the entire system toward the source. And we're measuring here a californium source 30 centimeters from the front plane of the detector. And if you can imagine a hinge along that x-axis there, that's where we will start to tilt our detector toward the source. And that will become more apparent in following slides. In order to make this simulation match more what we would expect when we perform experiments, we try not to take the absolute answers that are given to us by Polimi, and instead use behaviors that we have measured in previous experiments to Gaussian broaden our data. So assuming Gaussian behavior of light output and time of flight error, we can randomly sample distributions around the absolute values we obtain from our simulations, and in that manner broaden the energy deposited in our first detector and the time of flight within our system, and in that way get cones that are a little more realistic. And again, here's the time resolution distribution that we take to broaden our simulated data. So performing an image reconstruction at 0-degree elevation might look like this. The plane of our imager is completely in line with the source, and we make cones that look a lot like that, and our image looks like this. You can see that we can see a hotspot where the source is at 0, 0 degrees azimuth and 0 degrees altitude, but we still see those artifacts that we were talking about earlier, these cone structures on either side. What we want to do, what the goal is here, is to get rid of those using multiple scattering angles. So what if we reconstructed at a 45-degree elevation? So we've now tilted our imager toward the Californium source, and we get cones that look kind of like that. And performing a back projection with many of these different cones, we get something like this. So again, we have a hotspot around 0, 0. We also have a hotspot around 0 degrees and -90 degrees in the altitude. That's just because of how our cones look. So you can see that while one edge of the cone is pointing toward our source, the other is pointing almost straight down, and that's what we see here. So performing the same construction at several different angles, it goes from 0 degrees all the way up to eventually 9 degrees, which is not shown. But in 15-degree increments, you can see how the images change with the altitude angle of our system, and how we're getting very different cones at each angle. So summing across all these elevation angles, just summing the raw images, we get something that looks like this. And you'll notice that the artifacts are starting to blur out quite a bit because we're using such a larger variety of cones compared to one single image here. You might notice, though, that it's very extended below the hotspot at 0, 0. So we have these angles. What if we tilted the system down instead of up? Simply mirroring this image, we can obtain another symmetric problem where we have all of the complementary scattering angles instead by angling down. If we want to sum across all of these, we obtain an image that looks like this. And you can see that it's much more symmetric than this, which we started with by just measuring at one angle. So quickly concluding, I've demonstrated the effectiveness of a single array adaptive imaging system in simulation space, implemented broadening based on experimental data, and showed how important the lever arm distribution is in mitigating image artifacts. The expected impact of this work is a very compact, robust, and relatively cheap and low power imaging system, a deeper understanding of what causes image artifacts, and what kinds of cones that we want to take to get good images, and a demonstration of imaging using scintillators that were manufactured at Michigan. MTV impact, heavy collaboration with Sandia National Laboratories on creating organic glass scintillators. Both the materials and guidance for eventual casting of these scintillators came from Dr. Patrick Feng's group at Sandia Livermore, and also we've collaborated with Dr. Pete Marlowe also at Sandia Livermore on imaging. In the future, a system like this could go to a lot of interesting places around the DOE network. Our group has collaborated in the past with DAF at the Nevada National Security Site and Idaho National Lab to take images of some really interesting special nuclear material. So this is a potential avenue for the future with this system. Speaking of next steps, adjusting the altitude angle in smaller steps to more accurately simulate a continuously moving adaptive imaging system, manufacturing and characterizing organic glass cubes so that we can use the data, plug into our simulations, and eventually measure the neutron sources in the laboratory. So replicating these simulations in experiment and demonstrating that this imaging system works in real life. And finally, eventually implementing inorganics for gamma ray imaging. With that, I'd like to acknowledge NNSA and DOE for supporting the research activities, and I'd like to thank my NSF fellowship as well. And with that, I'll take any questions.
Thanks, Nathan. Nice talk. Questions in the chat. Can you talk a little bit about what you mean by handheld? Like what's the final size you envision for this imager?
So going back a bit, this IPM array itself is only about 2 by 2 inches. The electronics are rather small and simple. And one reason I included this down here is we currently use digitizers to read out all of our systems. And if we were to include a larger system, we would need a rack of digitizers. But here we can use something like this, which is maybe 8 by 8 by 2 inches. And so the whole ensemble, considering it's all low power, is something that you could feasibly fit in your hand.
Can you talk a little bit about the speed of the imaging process itself? In other words, how, if you had the system in a handheld form factor, how long would it take to, collect the data, process the data, and get the image? Is that a real-time situation, or would you expect some delays there?
At present, our data processing is not real time, but there's no reason that couldn't be implemented in the future. And that's it's a coupled problem to the system itself, but yeah, really there's no reason that it couldn't be real time.
Okay. Darren Holland asks, what are the benefits of this system compared to having a 3D array of detectors? So if you just had more detectors distributed in 3 dimensions, that would also improve the scattering out distribution. So can you talk about the benefits of this system compared to the other approach?
Well, one thing that's unique about this detector is that you can get more if you made your detectors 3D. For example, the HDPI accomplishes this by using bars, and in that way you have a continuous range of scattering angles. But it turns out that a system like this could actually get you more. And because you can continuously change the angle, you can get, well, first of all, an unlimited amount, but you can also explore a larger space of scattering angles than you even could if you were using something like bar detectors.
You mentioned this a little bit at the end, but Justin McIntyre is asking about neutron blind detectors for gamma imaging. So can you talk a little bit about the inorganics that you plan to implement and what that process would entail?
Sure. We've been looking at a few different materials. I think we've settled on serum bromide being a good candidate, but basically we have our neutron detectors. If we have a gamma ray scattered in an organic glass detector and then fully deposit in our cerium bromide, then we also have a Compton imager and neutron scatter camera in one.
I'm just reading this question that just came in. Neural commented about 1 in 3 faster detecting events due to room scatter. Okay, so can you talk a bit about room scatter in this device, and do you expect a similar or different results than what Neural was describing?
I have not done any room return measurements or anything, but I wouldn't imagine that it would be, well, there's less polyethylene like like is present in neural system with the large time-encoded mask, but there probably will be some room return. I'm not sure how bad the effect would be.
I had a question about the efficiency as a function of angle. So in this case, the reconstruction that you showed, did you effectively assume, I could use a simulator, right? So did you use the same number of particles for each angle, or how did you do that?
Did use the same number of particles. One thing that's important to note about the efficiency as a function of angle is that it depends a lot on your threshold. So when you have the system at a light angle like 0 degrees, you'll expect to see lower scattering angles, lower scattering angles, and so the energy deposit is not as high. And for low energy neutrons, that can cause them to fall below threshold. So it's maybe not quite what you would expect. It does vary significantly, but threshold is a big part of it.
Great. That covers everything in the chat. I'll just ask if anyone in the audience wants to ask a question. Feel free to please unmute yourself and ask away.
Just a quick question. I didn't follow why the cube detectors would be better than the bar detectors, because the bars can also be separated to increase the separations between scatters, and they do not have to be rotated to get samples of all different scattering angles.
Right. So the bars add additional complexity in terms of having multiple arrays and requiring additional calibration in order to perform position reconstructions along the bar. They're also more fragile. And so there's some concern for eventually deploying these in the field if we want to have large aspect ratio scintillators in our system.
Thank you. That's good.
Okay, great. Thanks everyone for the questions, and thanks Nathan for the talk. You can go ahead and release your screen.